somewhere in the unimaginable future, the last light flickers across the darkness. A single photon escapes the edge of a dying star. The galaxy it came from is long past its prime, its stars cold, its planets dead. There are no observers left, no life to greet it. It drifts through an ocean of silence, past the remnants of shattered solar systems, through the ruins of galaxies stretched thin by time, across a universe that has grown cold, dark, and empty. It is the final trace of a story that began 13.8 billion years ago, a story of light and fire, of chaos and structure and life, of atoms becoming stars, stars becoming worlds, and worlds opening their eyes. A story where, just once, a corner of the universe looked back and asked, "Where did we come from?" This is that story, from the first moment of time to the very last. This is the story of everything. In the beginning, there was no light, no matter, not even space or time. Yet, nothingness isn't truly nothing. Even a perfect vacuum seethes with ephemeral energy. Quantum mechanics forbids a state of absolutely nothing. In that primordial void, a tiny flicker, a quantum fluctuation, erupted. Some scientists have even suggested that our entire universe could be the result of a vacuum fluctuation, a momentary blip in a quantum void. In essence, it was as if a quantum egg of unimaginable potential cracked open, giving rise to everything. This was the Big Bang, but not a simple explosion in space. It was space itself unfurling, carrying matter and energy outward. Picture an infinitesimal spark in a silent abyss. No outside, no before, just a sudden emergence of energy from emptiness. In that instant, the universe was born from a paradox, something from nothing. The rules of classical intuition crumble here, cause and effect blur at the very moment of creation. It's a mystery that borders on the philosophical, a moment where existence itself tunneled out of the void, guided by quantum uncertainty rather than classical logic. What happened next defies the mind. In less than a heartbeat of cosmic time, that newborn speck of universe expanded ferociously, doubling in size again and again. This era, called cosmic inflation, blew up the infant universe from submicroscopic to gargantuan in a fraction of a second. In fact, the universe's size grew by a factor of about 10 to the 26th power, a 1 with 26 zeros, almost instantaneously, an expansion so fast that it outpaced the speed of light, since it was space itself, expanding, not objects moving through space. Imagine something smaller than an atom ballooning to astronomical scales in the blink of an eye. All the energy of that quantum egg poured out, stretching the very fabric of space like a canvas pulled taut. Any earlier irregularities or matter were smeared away by this extreme expansion, smoothing the young cosmos to near uniformity. Yet one thing remained imprinted: the tiny quantum fluctuations, microscopic wrinkles in space-time, were stretched enormously large. Inflation emptied the universe of anything that came before, except these quantum ripples, which it could not erase. Those ghostly imprints of randomness now speckled the cosmic canvas. During inflation's brief cosmic heartbeat, time itself was only just beginning. In quantum cosmology, time and space were intertwined in strange ways during this era. A new arrow of time was launched with the Big Bang's aftermath, giving the universe a direction from an initial state of quantum chaos. The very notion of before fades away. We're left with a profound mystery of a universe that began from an instant of no prior time, shattering our common sense notions of cause and effect. In that nascent moment, not only were matter and energy born, space and time themselves burst into existence. What emerged wasn't an explosion into empty space, but an expansion of space. The stage on which all physics plays, space-time unfurled from a single point, carrying everything with it. This breaks the mold of classical thinking. Every event we know has a before and after, but the Big Bang has no before in the usual sense. As Stephen Hawking and others have noted, asking what came before time began is meaningless, akin to asking what's north of the North Pole. Time had a starting point, and beyond it, before, has no definition. Consider that for a moment. Time, the ever-flowing river we drift upon, had a spring where it first welled up. In that first fraction of a second, time and space were newborn, woven out of quantum threads. The laws of nature, as we know them, were in their infancy. Even gravity and quantum forces were unified in an exotic state. To human minds, it's profoundly counterintuitive. How could the universe begin from essentially nothing, with no prior time to cause it? This is the quantum strangeness at our universe's origin, a realm where our logic falters, and we're left with humbled awe. The beginning of time feels less like a fiery blast and more like a transcendent awakening, where reality, as we know it, blinked into being. As inflation ended, its tremendous energy transformed into the matter and radiation of the young cosmos, a hot, glowing fog of particles. Within this primordial fireball, those subtle imprints from the quantum dawn, the tiny variations in density, set the stage for everything to come. Regions that were ever so slightly denser had a bit more gravity, pulling surrounding matter ever closer. Over time, those quantum fluctuations, stretched across the inflated universe, gave rise to density ripples, which in turn grew into the first stars and galaxies. In other words, the large-scale cosmic web of galaxy clusters tracing across billions of light years was seeded by microscopic quantum jitter in the universe's first moment. Without that primordial quantum noise, our universe might have remained an eternal, diffuse haze. In a perfectly smooth classical cosmos, nothing would coalesce. No stars to light up the darkness, no planets, no life. But reality is quantum at its core. Those minute irregularities were the fingerprints of creation. The seeds of matter that gravity later sculpted into galaxies, stars, and eventually us. It's a breathtaking thought. Every galaxy, every star, every living being owes its existence to tiny quantum fluctuations in that first split second after the Big Bang. The universe evolved from quantum weirdness into cosmic grandeur, from a featureless almost nothing into the rich tapestry of stars and worlds we see today. In the afterglow of the Big Bang, the infant cosmos carried a secret pattern, a delicate graininess that would one day become galaxies and galactic clusters, the cosmic web of night. From quantum randomness sprang all the order we know. The glowing fog would eventually cool and give birth to atoms. Atoms would gather into stars. Stars would forge heavier elements and collect into galaxies. In that moment of inception, the universe wrote the first chapter of a story that leads, billions of years later, to us gazing back in wonder. We are, in a very real sense, children of that quantum dawn. The strangest truth of all is that the universe's wild quantum beginning laid the groundwork for everything, for galaxies to spin, stars to shine, and life to emerge. In the cosmic dark, a spark of uncertainty lit the way for all the brilliance to come, and the echo of that moment still reverberates through every starry night sky we behold. After the Big Bang, the universe was initially filled with a blazing glow of energy, but about 380,000 years later, that glow faded into a cold afterglow, the cosmic microwave background, as the universe expanded and cooled. By this time, matter had settled into neutral hydrogen gas. There were no stars, no galaxies, and no new light yet. The cosmos entered a profound darkness known as the Cosmic Dark Ages, a period when no stars shone and space was black as coal. Why no light? In this era, the universe was shrouded in a fog of neutral hydrogen gas that could absorb or scatter any stray photons. Any light that was present, aside from the dim afterglow of the Big Bang, couldn't travel far. It would be like trying to see a lone candle through thick fog. The light was trapped close to its source. Effectively, the universe had no stars or cosmic beacons, and a dark veil of hydrogen hung over everything, hiding the cosmos in darkness. Yet, despite the blackness, important changes were brewing in secret. Much as Earth's own dark ages still fostered the seeds of a renaissance, the cosmic dark ages were a critical incubation period for the universe. During this time, the universe cooled from about 4,000 Kelvin to just tens of degrees above absolute zero. The gas was almost uniform, but not perfectly so. There were tiny ripples and slight densifications in the otherwise even spread of hydrogen, and a mysterious invisible mass called dark matter. These minute irregularities were the blueprint for everything to come. In the lightless calm of the cosmic night, gravity began to tug ever so gently on those denser spots, setting the stage for the first glimmers of starlight. In the absence of light, gravity became the master architect of the early universe. The distribution of matter, mostly dark matter with a sprinkle of hydrogen gas, was initially almost uniform, but tiny perturbations left over from the very early universe meant some regions had slightly more matter than others. Gravity slowly amplified those tiny seeds, pulling gas and dark matter ever closer in the denser regions while emptying out the gaps in between. Over millions of years, an invisible cosmic web began to form. Imagine a vast, three-dimensional spiderweb of matter with filaments of gas and dark matter stretching between nodes. Computer simulations show how threads of dark matter, which emits no light, and gas began to intertwine, forming a scaffolding of filaments and clumps. It's as if gravity were a patient sculptor, using the force of attraction to chisel structure out of chaos. This process was guided largely by dark matter, the hidden mass that neither emits nor absorbs light, but exerts gravity. Dark matter acted as an unseen hand that fashions the universe. It decided where matter would gather into clumps and eventually where galaxies would form. As one science writer put it, dark matter's gravity is what binds stars into galaxies and galaxies into galaxy clusters, sculpting the cosmic structure from the shadows. During the Dark Ages, dark matter clumped first, pooling into massive but invisible halos. These dark matter wells then pulled in clouds of hydrogen gas toward them. Slowly, the nearly uniform gas began to collect into dense, cold clouds at the centers of these halos. Imagine immense, dark proto-clouds of hydrogen, tens of thousands of light years across, gradually growing denser under gravity's pull. All of this happened in darkness. No stars yet flickered in these clouds, but deep in gravity's workshop, the conditions for the first stars were coming together. Gravity was gently squeezing and heating the densest pockets of gas. Eventually, those pockets would reach a breaking point, lighting a fire that would end the cosmic night. After roughly 100 to a few hundred million years of darkness, something revolutionary occurred. The first stars ignited. In the densest clumps of gas within those dark matter halos, the gas had become hot and pressurized enough for nuclear fusion to begin. Essentially, gravity's relentless squeeze sparked the first fire in the cosmos. A star was born. These pioneering stars are known as population 3 stars to astronomers, meaning the earliest generation of stars formed from pristine material. They formed in small groups within each halo, so the first galaxies were really just tiny clusters of these newborn stars shining together. When the very first of these stars ignited, it was like the universe took its first breath of light, puncturing the black curtain of the Dark Ages. One by one, more stars lit up across the cosmos, like scattered sparks in a vast dark sea. It wasn't an instant transformation. The darkness didn't vanish overnight, but the cosmic dawn had begun. The first stars were unlike most stars we see today. They were born from pure hydrogen with a dash of helium, lacking any heavier elements, which had profound effects on their appearance and fate. Key traits of these primordial stars included the monstrously massive. Because of the conditions of their birth, these first-generation stars were giants. Each could be tens or even hundreds of times the mass of our Sun. Some theories suggest a few may have grown to unimaginable sizes, perhaps thousands of solar masses in rare cases. With so much mass, they would have been colossal in size and gravity. In essence, these stars were giant beasts, composed only of hydrogen and helium. Blindingly bright and hot, a star's mass fuels its luminosity, and these behemoths burned fiercely. A single population 3 star, hundreds of times more massive than the Sun, would shine millions of times brighter than the Sun, emitting searing ultraviolet light. They likely glowed with a brilliant blue-white hue due to surface temperatures of tens of thousands of degrees. Their intense ultraviolet photons began carving into the surrounding gloom, stripping electrons off nearby hydrogen atoms and creating bubbles of transparent, ionized gas around them. Ephemeral lives. These massive stars lived fast and died young. Where a star like our Sun lives for billions of years, a POP3 star's life was incredibly short, on the order of only a few million years or less. They were short-lived candles that burned through their nuclear fuel at a breakneck pace. In fact, astronomers estimate many of them perished in under 1 million years, an eye blink on cosmic timescales. Cosmic alchemists. Despite their brief lives, these first stars had a lasting legacy. Inside their cores, for the first time, nuclear fusion forged heavier elements like carbon, oxygen, silicon, and iron out of pure hydrogen and helium. And when they died, they exploded spectacularly. Many ended their lives as titanic supernova explosions, spraying those newly forged elements out into surrounding space. In those violent deaths, star stuff was scattered into the cosmos, seeding the primordial gas with the first dusting of heavy elements. Some of the very most massive may have died in even more energetic hypernovae, or collapsed directly into black holes, seeding the centers of what might later become galaxies. The agents of change. These stars didn't just enrich the cosmic gas. Their intense light started to change the state of the universe. The ultraviolet glow from these stars reionized the hydrogen around them, meaning it turned the neutral hydrogen atoms back into charged particles, protons, and free electrons. This was crucial because ionized hydrogen no longer trapped light the way neutral hydrogen did. In effect, the first stars began punching holes in the cosmic fog, creating expanding bubbles of transparent space through which light could travel. They were the heralds of a new era, paving the way for a transparent, light-filled universe. Each population 3 star, therefore, was a beacon of transformation. For a brief moment, it would shine intensely in the darkness, illuminating its corner of the universe. Then, in a brilliant demise, it would enrich the cosmic gas and clear the way for the light of future stars. Though none of these first stars have survived to the present day, they burned out so long ago, their fingerprints are everywhere, in the heavier elements we find in later stars, in distant galaxies' light, and even in the atoms that make up our own planet and bodies. The first stars were truly the first lights and first heavy element factories of the cosmos, and they set in motion the chain of events leading to the world we know. As the first stars appeared, they were not isolated lone actors for long. Gravity continued its work, now on a larger canvas. The same dark matter halos that birthed the first stars began to collect groups of stars together, forming the first protogalaxies. We can think of a protogalaxy as a small, nascent galaxy, perhaps only a few million stars or less, dwarfed by modern galaxies, but significant as the first organized systems of stars. The stars in each early halo were bound together by gravity, orbiting within the clump of dark matter that had pulled them in. In effect, the dark matter provided an invisible scaffold on which these early galaxies were built. These newborn galaxies were faint and tiny compared to the majestic spirals and ellipticals we see around us today, but they marked the dawn of galactic life in the universe. As more stars rapidly formed and died within them, these first galaxies shone and flickered, growing in mass and brightness. When a massive star died in a supernova, it would blast heavy elements into the gas of its host protogalaxy. That gas, now enriched and stirred, could cool more efficiently and condense again to form new generations of stars, including slightly smaller, longer-lived ones. Thus, the first galaxies became cosmic nurseries, recycling the material of the first stars into new stars. Over time, neighboring small galaxies would also pull toward each other and merge, assembling larger structures. In this way, galaxies began to grow. A tiny protogalactic cluster of stars might merge with another, or draw in fresh gas along the cosmic web filaments, sparking new rounds of star formations. Through countless mergers and accretions, larger galaxies gradually took shape. Hundreds of millions of years after the first stars, some second-generation galaxies were already much heftier and brighter. Once the ambient hydrogen gas had been largely ionized by the light of earlier stars, gas could fall into even bigger, dark matter halos without impediment, leading to the formation of more massive galaxies. Eventually, given enough time, massive galaxies like our Milky Way would be able to form in those huge halos, though that process took billions of years. But by 1 billion years after the Big Bang, the universe was no longer a void of darkness. It was a cosmic city of fledgling galaxies, glowing with starlight and starting to resemble the structured cosmos we see today, just on a smaller scale back then and still rapidly evolving. Crucially, as these early galaxies lit up, their combined radiance achieved something universe-changing. They pushed back the dark fog entirely. Each galaxy, full of young hot stars, created a bubble of ionized, transparent space around it. As more and more galaxies formed and grew, these bubbles expanded and merged. Before long, instead of isolated pockets of clarity, vast regions of the universe became clear of hydrogen haze. Light could travel freely for the first time since the Big Bang's afterglow. Astronomers refer to this major transition as the epoch of cosmic reionization. But in simpler terms, it's the moment the cosmic dawn truly broke. The cosmic dark ages gradually gave way to a universe flooded with light. One source describes how overlapping ionized bubbles from infant galaxies eventually filled the whole universe, bringing the dark ages to an end. In other words, the night that had lasted hundreds of millions of years was over. A new day in the universe had begun. The emergence of the first stars and galaxies was the universe's grand turning point. What began as an opaque, lightless abyss was transformed into a sparkling expanse of stars. Bit by bit, gravity's patient sculpting paid off. The tiny ripples and density became clusters of matter. Those clusters gave birth to brilliant stars, and those stars assembled into the first galaxies. With that, the lights came on in the cosmos. One astronomer aptly said, "The first stars and galaxies formed, and their light brought the universe out of the dark ages." It is hard to overstate the drama of this transformation. Imagine a universe with no light at all, silent and black for eons, and then the first gleam appears. Then another, and soon a whole tapestry of early stars and galaxies is twinkling. It was truly like a dawn breaking over an endless night, the first sunrise in a universe that had never seen day. Now let's see what the lights revealed. This dawn of starlight not only illuminated the cosmos, but also set the course for everything to come. The heavy elements forged and dispersed by those first stars would eventually form new stars with planets around them. From those ingredients, galaxies like our own Milky Way would grow, and planets like Earth would coalesce. In a very real sense, we owe our existence to that early light. Black holes, neutron stars, even life eventually here on Earth, the roots of it were planted in the dark ages. When we gaze up at the night sky today, filled with the glow of billions of stars and galaxies, we are witnessing the enduring legacy of that long ago epoch. The cosmic dark ages gave way to cosmic dawn, and in that brilliant new light the universe began a complex journey of growth and evolution. Ultimately, this epic transition from darkness to the first stars, and from those stars to the first galaxies, transformed the universe forever. What was once a dark, simple cosmos became a radiant, structured universe teeming with stars and galaxies. It's a story of creation and illumination, of gravity sculpting masterpieces out of primordial simplicity. In the glow of the first stars, the universe awakened and the cosmos blossomed with light. This was the moment the great cosmic dawn broke, the first chapter in the story of stars and galaxies, and the moment when the deep night of the early universe finally yielded to a sky filled with starlight. The stage was now set for all later cosmic wonders, from the formation of familiar galaxies to the emergence of life itself, all thanks to that first dawn that ended the long, dark night. In the silent darkness between stars, great cosmic clouds glow with unearthly shapes, twisting towers of dust, luminous ribbons, and bubble-like shells. These ethereal veils of gas and dust are nebulae, and they tell a story of cosmic renewal. They can be the birthplace of new stars and the remnants of dying ones. Every star's life is a chapter in this endless cycle of creation and destruction, a journey that begins in a nebula's embrace and ends by enriching space with the ingredients for new stars to come. Stars are born within vast, cold nebula, often called molecular clouds, stellar nurseries holding thousands of times the sun's mass in gas and dust. Deep within these dark clouds, gravity draws clumps of material together. Bit by bit, a dense pocket of gas grows, its gravity strengthening as it pulls in more mass. Eventually, the clump collapses under its own weight, contracting and heating up from the friction of infalling gas. In this crucible, a faint embryonic star, a protostar, begins to form at the cloud's center. Towering ridges of gas and dust in the Carina Nebula's star-forming region, the cosmic cliffs, glow with the light of young stars carving out cavities in their natal cloud. These breathtaking structures, observed by the James Webb Space Telescope, illustrate the stellar nursery environment where new stars take shape from clumps of cosmic gas. Such nebulae appear as celestial landscapes with mountains and valleys of dust sculpted by starlight in the darkness of space. For tens of thousands of years, the protostar continues to gather material and grow. When its core becomes hot and pressurized enough, a miraculous transformation occurs. Nuclear fusion ignites. Hydrogen atoms begin fusing into helium, releasing a flood of energy. A star is born, shining with stellar fire and pushing back against gravity's crush. The newborn star's radiation blows away the cocooning gas, ending its gestation. What remains is a brilliant young star amid a dispersing cloud, often not alone, but alongside sibling stars born from the same cloud in a stellar cluster. Once ignited, a star enters the long, stable phase of its life known as the main sequence, steadily burning its hydrogen fuel. How long a star shines and how brightly it burns depends on a single factor: its mass. Small, low-mass stars sip their fuel slowly, glowing dimly and living for billions or even trillions of years, far longer than the current age of the universe. Enormous, high-mass stars, in contrast, blaze through their fuel at a furious rate. They shine hot and blue-white, but may exhaust their core hydrogen in only a few million years. In this way, a star's mass is its destiny, dictating the course of its life and the drama of its death. The quiet death of low-mass stars. After a long life warming the cosmos, a sun-like star's fuel eventually runs low. When a low-mass star, like our Sun, exhausts the hydrogen at its core, it faces a gentle undoing. With fusion slowing, the core begins to contract under gravity. The star's outer layers, however, expand outward, turning the star into a swollen red giant. In this bloated phase, the star's light reddens and its heat is spread over a vast area. Deep inside, the star fuses helium into carbon, but this too is only a temporary reprieve. the aging giant becomes unstable and begins to shed its outer layers in pulses. Each pulse is like a faint heartbeat, pushing the star's gas outward into space. Finally, the star puffs off its last outer shells, casting them adrift into the void. All that remains of the star's former glory is an expanding, glowing cloud of gas and dust, a beautiful planetary nebula. The Helix Nebula is a ghostly cloud formed from the cast-off layers of a dying, sun-like star. Often called the Eye of God nebula for its appearance, it represents the final breath of a low-mass star as it gently expels its outer atmosphere into space. At the center of the Helix Nebula lies a tiny point of light, the star's exposed core, now a white dwarf, which glows like a faint ember amidst the stellar ashes. In time, the nebula's gas will drift away into the surrounding interstellar medium, carrying with it the elements that the star forged in its lifetime. At the heart of the planetary nebula, the star's core remains behind, stripped of its outer layers. This core is now a white dwarf, a small, hot, stellar remnant about the size of the Earth. It no longer produces energy from fusion. It simply cools and fades very slowly over billions of years, yet a white dwarf is far from delicate. It contains a mass comparable to the Sun packed into an Earth-sized sphere, making it incredibly dense. In fact, a single teaspoon of white dwarf material would weigh more than a pickup truck here on Earth. The white dwarf is the quiet cinder of a star, a cosmic ember fated to glow faintly for eons. Meanwhile, the gaseous shell it shed, the planetary nebula, expands and disperses into the galaxy. Even in this gentle death, the star returns its substance to space, seeding the cosmos with elements like carbon and nitrogen that it created in its core. It is a serene finale. A star dies not with a bang, but with a whisper, leaving behind a shimmering memory of what it once was. For the giant stars, many times heavier than the Sun, death is a far more violent affair. A high-mass star lives fast and dies young, and when its end comes, it is spectacular. After burning through its core hydrogen in mere millions of years, a massive star swells into a red supergiant, hundreds of times larger than our Sun. Deep inside its contracting core, ever more furious fusion reactions occur in sequence. Helium fuses into carbon, then carbon into neon, oxygen, silicon, building layered shells like an onion. Each stage burns hotter and faster than the last, and each yields heavier elements. Finally, the core's fuel reaches the limit. It produces iron, an element it cannot fuse for energy. In that instant, the star's balancing act collapses. With no outward pressure to oppose gravity, the iron core implodes. In a fraction of a second, the core is crushed into an extremely dense state, then rebounds outward violently. This unleashes an immense shockwave that rips through the star. The star's outer layers are blasted into space in one of nature's most powerful detonations, a supernova explosion. What was once a steady star is now a brilliant and bright catastrophe. For a few shining weeks, a supernova can outshine an entire galaxy of normal stars. In those brief moments of chaos, new elements are forged in the furnace of the explosion. The incredible energy of the blast slams lighter atoms together to create heavier ones beyond iron on the periodic table. Gold, silver, iodine, uranium, all the rare elements heavier than iron, are synthesized in the fiery crucible of a supernova and then hurled out into space. The exploding star thus seeds the cosmos with a treasure of newly minted atoms. All that remains of the star itself is its shattered remnants, an expanding cloud of gas and dust racing outward, and a dense core deep at its center. A supernova remnant marks the violent death of a massive star. Shown here is the glowing debris cloud of a star that exploded in the year 1572, an event witnessed by astronomer Tycho Brahe. Modern telescopes reveal an almost spherical shell of stellar ash expanding into space. In this false color image, X-ray and optical data show the shock waves in blue and green, and heavy elements in red and orange moving outward at millions of miles per hour. Such supernova remnants scatter the star's contents into the cosmos, seeding the interstellar gas with the chemical elements that the star forged over its lifetime, and in its explosive death. In the heart of the wreckage, gravity crushes the former star's core into an extraordinary object. If the original star was not extremely massive, roughly up to 8 to 20 times the Sun's mass, the collapsing core is halted by the formation of neutrons, and it becomes a neutron star. This neutron star packs more mass than our Sun into a sphere only about 20 kilometers across, about as wide as the city of Manhattan, making it so dense that a single spoonful of neutron star matter would outweigh Mount Everest. The neutron star is a bizarre stellar corpse, often spinning rapidly and shooting out beams of radiation as a pulsar, like a lighthouse in the darkness. If the star was even more massive, however, nothing can stop the core's collapse. The core continues to crunch inward until it vanishes from view, forming a black hole, an abyss of gravity where the star's mass is concentrated into an infinitely dense point. Not even light can escape the grasp of a black hole. In either case, neutron star or black hole, a massive star's death leaves a striking relic. It is a dramatic end, not a peaceful fading, but a spectacular burst that blows the star apart and drastically reshapes its surroundings in the blink of an eye. The story does not end with the remnants of a star drifting through space. In fact, these very remnants are the seeds of new cosmic beginnings. When stars die, whether by gently puffing off their shells or by exploding in supernovae, they return their material to the galaxy. The gas and dust cast into the cosmos by dying stars enriches the great cosmic clouds with heavy elements. Over time, this dispersed stardust mixes into other nebulae, seeding them with the ingredients for future stars and planets. It's all part of a grand cosmic recycling process. Each generation of stars contributes the chemical building blocks for the next generation. And one of those generations gave rise to a planet that's close to all of our hearts. In the early universe, the primordial gas was mostly hydrogen and helium. It was the lives and deaths of stars that fused and scattered the rest of the elements that now fill the periodic table. Every carbon atom in your body, every calcium atom in your bones, and every iron atom in your blood was forged in the nuclear furnace of some long-ago star and blown into space by a stellar explosion. "We are made of star stuff," the astronomer Carl Sagan famously said, and he was exactly right. The atoms that compose us and everything we see around us come largely from previous generations of stars. The death of those stars billions of years ago paved the way for our own existence. Supernovae, in particular, are one of the original sources of the iron in our blood and many other elements essential to life. Thus, in each stellar death lies the promise of new life. The heavy elements scattered by dying stars, oxygen, carbon, iron, and beyond, will drift through the galaxy until gravity draws them into a new cloud, a new star, a new world. Nebulae that are enriched by ancient stardust eventually condense to spawn fresh stars, continuing the cycle unbroken. In time, one such enriched cloud will collapse and give birth to a new star system. In this way, the ashes of dead stars become the nurseries of newborn stars. The cosmos constantly renews itself, an age of death and rebirth, woven into the very fabric of the galaxy. Stars are not immortal, but through their deaths, they become the creative force for new stars and new possibilities. The stage is thus set for the next chapter of the cosmic story, as the dust and elements from countless dead stars come together to form new suns and new worlds in an eternal cycle of cosmic resurrection. Every sunset of a star carries with it the dawn of new celestial beings. In the grandeur of deep time, we witness stars as both creators and destroyers, brilliant furnaces that build the elements and fiery titans that sow those elements back into the galactic soil. It is a humbling, almost spiritual vision, the universe recycling its stars, turning death into rebirth over and over. As we gaze up at the night sky, we are looking at a cosmic garden in which each bright star was born from the death of others. And somewhere in that glittering tapestry, long ago, the ingredients for our own sun and planet were scattered, waiting for their moment to shine. The age of death and rebirth is the universe's way of reminding us that endings are also beginnings, that in the cosmic drama, every death fuels new life among the stars. About 4.6 billion years ago, our planet Earth coalesced within a swirling disk of dust and gas encircling the newborn sun. In this chaotic nursery of the solar system, countless rocky fragments collided and merged. Earth grew larger with each impact, a violent accretion that climaxed when a Mars-sized protoplanet, often called Theia, slammed into the young Earth. The cataclysmic collision blasted a huge cloud of debris into orbit, which eventually coalesced under gravity to form. This newly formed moon's gravitational presence helped steady Earth's wobbling tilt, stabilizing the climate and seasons, a crucial factor that would allow life to take hold. In its infancy, Earth was a hellish world. The heat from incessant impacts kept the surface molten. A global magma ocean, hundreds of miles deep, covered the young planet. No solid crust or tranquil seas existed yet. Any water was vaporized into an eerie steam atmosphere by the scorching heat. The early sun shone dimmer than today, but unleashed fierce solar winds and radiation across the battered Earth. As eons passed, the bombardment waned and Earth began to cool. Dark, solid ground congealed from the liquid rock. Rain fell for the first time in ages, filling the deepest craters and basins with water delivered by countless comets and volatile-rich meteors. Thus were born the first oceans under a cloudy sky. Though born in fire and chaos, the planet now had both a stable rotation and liquid water, gentle conditions compared to its violent birth, setting the stage for an even greater miracle to come. From the chaos of Earth's formation, life took root in its oceans, simple, microscopic organisms that clung to existence in a world of fire and water. Over billions of years, they transformed the planet's atmosphere, setting the stage for greater complexity. Life grew bolder. It developed eyes to see, limbs to walk, shells to survive. It crept from the seas onto the land, adapting, diversifying, enduring. Through cataclysms and extinctions, the story of life never stopped evolving. Dinosaurs ruled, then vanished. In their shadow, small mammals endured, waiting patiently for their chance. That chance came 66 million years ago when the skies fell and the Earth changed. In the silence that followed, those mammals inherited a broken world and began to reshape it. From one humble branch of this mammalian family, something extraordinary emerged. By around 300,000 years ago, anatomically modern humans, Homo sapiens, had evolved in Africa. They looked like us. Their hands could shape art and weapons, and their vocal cords could share stories. These humans spread out of Africa around 50,000 years ago, journeying into Asia, Europe, Australia, and eventually the Americas. Wherever they went, they adapted and survived, even as they encountered ice ages, strange beasts, and new lands. They painted hauntingly beautiful images of animals and symbols on cave walls, hinting at an emerging imagination. They learned to make fire, sew clothing, and craft languages to communicate ideas both concrete and abstract. With the end of the last ice age, our species turned to cultivation. The dawn of agriculture, about 10,000 years ago, led to the first villages and then cities. In a relative blink of an eye, humans developed civilization, writing, culture, science, and technology. We built monuments that touched the sky and ships that crossed oceans. The descendants of ape-like creatures had become self-aware thinkers, capable of exploring not just the world around them, but the world within their minds. Through us, the raw, ancient force of life had blossomed into consciousness, the ability to ponder origins and endings, to seek meaning in the stars. Now, at the culmination of this epic journey, picture an astronaut standing on the moon in 1968, raising a camera to capture a mysterious sight, a blue-white Earth rising above the lunar horizon. Earthrise, as this famous photograph came to be known, revealed our world as a fragile oasis of life against the black backdrop of space. The iconic Earthrise photo taken by Apollo 8 astronaut Bill Anders. It shows our tiny blue planet peeking over the barren lunar horizon, a stark reminder of the rarity and preciousness of Earth in the cosmic void. In that image, and in countless observations since, we see that our Earth is but a pale blue dot, a solitary, improbably fertile world in a vast, dark cosmos. All the fire and drama of Earth's formation, all the struggles of life's evolution, have led to this, a world that can look back at itself with understanding. The fact that we humans can trace this story, that the universe has, in a sense, become aware of itself through us, is a profound wonder. Scientists and philosophers refer to this realization as the anthropic principle, the notion that the universe's fundamental properties must be compatible with the emergence of conscious life. Otherwise, we wouldn't be here to observe it. After all, only a universe that allowed galaxies, stars, planets, and eventually living minds to form could ever be seen and contemplated. In the poetic words of astronomer Carl Sagan, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Indeed, the very atoms of our bodies were forged in long-dead stars and scattered across the galaxy, only to regroup on a cooling Earth and begin to think and feel. Across 4.5 billion years of tumultuous history, a chain of events, each unlikely on its own, led to the rise of conscious beings who can gaze up and marvel. Through our curious eyes, the universe observes its own majestic unfolding. Through our minds, it wonders why and how. And so, the story of Earth is the story of the cosmos awakening to self-awareness. A tale as improbable as it is inspiring. A tale that reminds us that we are truly children of the stars, beholding the very stars themselves. And through this gift of sentience, it falls upon us to not squander this gift of life, to not be consumed by petty differences, which often amount to meaningless doctrine or some other such triviality. For in the end, if through our intransigence we allow this spark of life to be snuffed out, it will amount to a crime for which there can be no forgiveness, even if there is no one left to forgive, save for the countless wonders that were missed due to the worst side of our nature. We must instead unite to explore the universe in all its glory and might, and embrace a future we can explore together. And speaking of the future, that's what we'll be exploring in part 2, and I mean the far future. Heat death, big crunch, and all the rest of it. I really hope you enjoyed this latest stellar story. Remember to like and subscribe, and I'll respond to your comments. See you next time.